So let me kind of summarize and ask this question again. For brevity, I'll call this R. There's no particular reason you should know this. I just gave it to you as a given. If you want to know how to discover these things, we can talk about that later. But it turns out that the product of non-principal ideals is ideals is principal, but because the class group is C2, the product of two non-principal ideals has to be principal. And of course, the product of a principal and non-principal is non-principal. Class number 2 is kind of an interesting thing. So I asked last time, I want to find primes with the following two conditions. Number 1, minus 5 is a square. On P. And number 2, P cannot that is to say P is not a norm. We say not the norm of an element Anybody find one?
I thought last time you asked for one that's not a square one.
Let's see. Maybe I did, but actually it doesn't matter because they're, if you can tell me all the ones that are squares modulo P, I can tell you the rest of them will be non-square, or complement will be things that are not squares. Okay. Anybody? So I want minus 5 to be a square modulo P. Anybody?
29.
So minus 5 is a square mod 29, right? Let's see if that's on the right list. I think you're right, actually. In fact, generally, you could go through and kind of cherry pick some of them just by pencil and paper, working it out. Generally, the primes P for which minus 5 is a square mod P R of the point. P is equivalent to 1, 3, 7, or 9 mod, so Eric, there's your 29 right there, right, because it's equivalent to 9 mod. Basically, this follows from some stuff in number theory about splitting primes and so forth, so on. It turns out that, where does this come from? This is kind of the final answer. You need, so this might, if you want to puzzle over this and try to figure out why this is true, you can certainly figure out that this is a necessary condition pretty quickly. I can go over this later. I'll just tell you what the solutions are now. What you need is P is equivalent to 1 mod 4, and P is equivalent to 1 or 4 mod 5, or P is equivalent to 3 mod 4, and P is equivalent to 3 mod 5. That's basically what it boils down to. This follows from quadratic reciprocity. You can also do this in a more bulldozer fashion. But notice what happens here. The P's that are equivalent to 3 mod 4 are the ones where -1 is not a square mod P. And notice that 2 and 3 are non-squares mod 5. Here 1 is a square mod 4, and 1 and 4 are the squares mod 5. Basically, this gives you your solution mod 20. You don't need to really know all this. I'm just kind of painting the background for you. How do I get from here to here? Right, these two conditions to this condition mod 20. Oh, well, it's a Chinese remainder theorem. Right, hence 4 times 5 is 20. So this is condition 1. Condition 2 also enforced 2. That is to say, we want that condition as well. Well, if P cannot be written in this form, well, if P can be written in this form, then P must be a square mod 5. Everybody agree with that? So if you could ever write x squared plus 5y squared is P, mod 5, you must have that x squared is equivalent to P mod 5. So P is a square mod 5. So let's enforce P is a non-square. That is, P is equivalent to 2 to 3 mod 5. And of course, I'm always ignoring the prime 5 here. So if we enforce this condition in tandem with this one. So let's say that I want P to be 1, 3, 7, or 9, mod 20. And I also want it to be equivalent to 2 or 3 mod 5. Right? So here are our usual suspects. All right. You can toss these two as being kind of throwaways. So let me give you kind of a small list of this. So here are my usual suspects: 3, 7, 23, 23, 43, 47, 67, 83, 103, 7. Now, you can check, for example, here's a simple one. For 3, you can't write that as the sum of the square and 5 times the square, 7, all these as property. Pick one out of my list of primes here. 23, pick another. 83, you're evil. Well, let's see, what is that gonna be? 1600, 1829 or something like that. Right? Right, doesn't it?
1909.
Yeah, it's 1909. Where did that go?
I totally did that in my head.
I promise you that that is a square plus 5 times a square. Anybody see how to do it? I don't need it. Let's fit it out. Right? I guarantee it. It's not a square by itself. Subtract 5, subtract 20, etc., etc. Anybody get it? I guarantee it's there. I like this example. This is taking a while. You're not gonna let me beat you, are you? All right. Okay. Uh, okay, so. Okay. So let's try 5, let's try 6, 180. Oh, there it is, that's gonna be it. Oh, no, it's not, it's just, cool. Okay. 7 squared, so 49 times 5 is, what, 245? Not it. 864, that's what, 320?
Y18 from X17.
Okay, so that was a nice one in the middle. So you guys picked one right in the middle of it. It'll take me a little while to get there, huh? So that's 324 times 5, which is 1,500 something plus what, 289 is that? Guaranteed. I mean, let's take one that's easier. Take 7 times 23. This is 161. This is 5 times 16 plus 81. So this is 9 squared plus 5 times 4 squared. This always works. If you take any pair of these primes, none of them can be represented in the, none of these can be written as a square, it's 5 times a square. Yet, if you take the product of any two of them, in fact, if you take the product of any even number of them, then you'll be able to write it that way. So you might know why.
Class group. What are going on here?
That's right. Each of these primes each prime of this fails to be prime in the larger range. So P actually factors into
Why does it fail to be prime?
because of this because of these conditions right here. The two conditions here. And I can go over that later if you like, but the norm of P is P squared, right? That's true for any rational prime. And this is the norm of P1 times the norm of P2. There's a natural way to extend the notion of norm to an ideal like this. What does that say about the norms of each of these? Well, if the norm of the product of these two, if you give me these are both integers, and the product of these two have to be P squared, they both have to be P. The only other alternative is 1 and P squared, but it turns out that if, just like with an element, if you have norm of an ideal is 1, that means the ideal is the whole ring, which is not the case here. So if you take 2 of these things, these are non-principal ideals. And what do we say in this ring happens when you multiply any two non-principal ideals to a principal ideal? The norm of this one is PQ. And this is a principal ideal, which means out there somewhere is an element. We found it here for this one right here, the complicated one. It was 17 plus 18 radical negative 5. There's the element whose norm is exactly what's predicted. So this is a nice application of class groups. It's used in classical number theory problems like representation of various integers, more specifically primes, in terms of quadratic forms, and it shows up in things all over the place, coding theory and the like. Okay, so let me give you another example. We're going to be kind of chock full of examples today. Get through them. Here's another quick example. It's 4. So. So my first question here is, if I know the class number, if I know the order of the class group is 4, how many choices for, up to isomorphism, how many groups are there of order 4? There's 2, so that means that, that now it turns out, let's see how I want to phrase this here. Um, all of the prime ideals except for the trivial ideal I'll put in the principal class. Okay. Here is my question. Is this Z2, Z2, or Z4? And how can you tell? I'm gonna call these just for convenience, Q1, Q2, Q3.
Yeah, probably check the order.
Okay, so notice that
You know that all of those are distinct.
you'd have to check that. You'd have to check that. Can somebody give me a more compact way? Outright, this, everybody agrees the ideal is in about 3. Certainly 3 divides everything here. And because I've got a 9 and a 15, I've got the greatest common divisor in the integers, which is 3, right? So these two are in inverse classes. It's easy to check that if you square this one, you get the ideal generate by 2. That one's not too difficult to check. It's got your generators. So these two are inverses. This one squares the identity. So what does that mean? That means either these two elements, well, if I told you they're in different classes, if I told you in different classes, that already means it's Z4, right? Because these two are inverses of each other. And if it was Z2, Z2, that'd be the same class. But let me check this more directly. What happens when I square 1? This is 9, 3, and square of this, which is whatever that is, that's minus 13. That's 2 radical. Now suppose Then the norm of alpha is equal to the norm of p squared, which is 3 squared, which is 9. This p, or I should say p1. Because p1 times its conjugate here is 3, so that means product of these two is 9, so each of these has norm 3. Now, alpha, let's write alpha down, let's call it x plus y bracket negative 14. Notice that the norm of alpha is x squared plus 14y squared. Now let's suppose that the norm of alpha is 9. How many solutions to x squared plus 14y squared equals 9 do you have? Well, one interesting one, right? Because really your hand is forced. The coefficient or the multiple of 14 has to be 0, right? And that forces y to be 0 and x to be plus or minus 3, right? So there you go. Notice that P1 squared is not the ideal generated by 3. I'm sorry, it's not the ideal generated by 9. Let's see, P1 squared is alpha. Then the norm of alpha is so let's see, the norm of alpha should be the norm of P1 squared, which is oh. Notice that P1 squared is not this, because it's certainly true that 3 divides this and this, but 3 does not divide this. And so this is the only possibility for a generator of P1 squared that's principal. So this has to be a non-principal ideal.
How did you know the norm of P1 is 3?
It's the same argument as we gave over here, because if the norm of this is 9, that means the norm of this times the norm of this is 9. So that means that both of these have to be norm 3, or one of them is true. Let me give you a theorem before I do one last example here. I've been dying to give this for a couple of days, and I've just gotten carried away on doing some of these other applications here. This is kind of a neat thing. I throw this theorem in because it goes beyond this number theory. Now I'm going to go back to one more number theoretic example before we move on from that. Theorem. Let be Dedekind with quotient to it. Let F be an algebraic extension. K that is root closed. And let me tell you what I mean by that. For all alpha in F and N in natural numbers, alpha to the 1 over N, then F. So in other words, it contains all its nth root. This is something that's a little bit perhaps more general than algebraically closed. It doesn't have to be algebraically closed necessarily, it just has to contain nth roots of all the elements that are in there. If every field intermediate between K and F have ring of integers with torsion class. Then then T, the interval closure of R and F is basic. So let me give you let me give you let me the application here. As a matter of fact. Uh, This is something that I claimed very early on in this class, and now, once we're on with this theorem, we'll be able to prove this. The ring of all algebraic integers, so this is a classical ring of all algebraic integers, is in fact basic. So let me prove the corollary, and I'll prove the theorem. Z bar is, of course, the interval closure of Z and Q bar. This is the algebraic closure. So, of course, Q bar satisfies the hypothesis because if you have any element of the algebraic closure, it's algebraically closed, so it contains all its nth roots. And I need to make a stronger statement here. Didn't write that in my notes here. I need one more thing here, so I'm glad to correlate first. Every field intermediate between K and F, let me call E intermediate, such that E over K is finite. The theorem that I wrote is true as follows, but you don't even need all that. What I originally said is every intermediate field has to have ring of integers with torsion class group. No, you actually can do something more general than that. You only need to check the ones that are finite.
What do you mean by torsion?
Everything has finite order,
Okay.
right? So if you have So if you have an intermediate field, then R, a ring of integers, has not just torsion, it has finite clusters. That's one of the facts that I gave you last time. That if this is a finite extension of Q, then a ring of algebraic integers formed by this actually has a finite class group, and there's actually infinitely many primes in every class, right? We only need the fact that it's finite, and finite implies torsion. Hence, by theorems, so let's prove this. Let's prove the theorem because it's gotten us a major result. It's not clear, right? I mean, there's an awful lot of ideals in there. I'd hate to have to check them all. So this theorem does a lot of work for us. Let T be the ring of integers. F. T is the closure of R and F. Let be finite. So what we want is we need to show it's basic, we need to show that this finitely generated ideals. Principle, so let's let I equal A1, A2, AN. Okay. Now, the first thing I'm gonna do is now consider these, of course, these elements are all integral over Z. So take your base field K, right? So I'll draw a diagram here, R inside K, and now I have K1, K is joined with A1 up to AN. Notice that this is finite, as a statement here, right? And so it's finite, so it's an algebraic extension of K. And it's got ring of integers T1. Okay. Consider its ring of integers T1. So let's look at this ideal extended up here. What do I know about this? Well, there exists M in the natural numbers such that such that I have to be M's principal. Where do I get this? This uses the fact that the class group is torsion. So this thing has finite order in the ideal class group. So there's an nth power of this that is principal. Agree? Okay. Now that I've got that taken care of, now and there's where I need my nth roots. Now I'm going to go to K2, the toughest one. by taking an extension of that. Right. Now, in this. Okay. In K2, what happens is. Um, again, this should still hold, right? And this is. Because now, in the ring of integers two, we have a to the 1 over n power. Therefore, I have, and how does this last step follow just by taking this? That's because I can decompose I hat into a product of primes uniquely. I cannot decompose this into a product of prime ideals uniquely. They all have to be in power, so you strip it down and you get this. So that means that this ideal that we had here at T, it sort of first rears its head here when you've got the generators for it. But then when you get up this far, it becomes principal. And once it's principal here, it's principal all the way up. And that's all you need right there. So this is a really, really cool theorem. So if every finite extension has torsion class group, then you've got a basic domain. Okay. Any questions? Okay, I've got time for one more example, which I think I have to give you all. So in this example, okay, we just sort of went over this a little bit. The class group is C4. So I'm going to write this way. I know that's additive, but 0 means the principal class. These are the ones that are already principal. This is a generating class, and this is its inverse. These two, and this is the class order 2. For my notation, these are in 1 bar. Q's are in 3 bar. So these two are in opposite classes, inverse classes, and M's are in 2 bar. So it takes a 4th power to make a P principal, and it takes a 4th power to make a Q principal, and squaring an M makes it principal. X2 equals what I'm trying to illustrate in this example is why the class group might be important if you're considering factorization. So what you might have taken away from this so far is that, okay, there are these classical examples of things that don't have unique factorization. Well, these Dedekind domains have unique factorization in prime ideals. How does this affect the kind of elemental factorizations you might see? How many factorizations do these have into elements? This only has one, up to associates, up to mucking around with by units. Basically, and so, this basically only has one. Up to a unit, this is just y times y. Because it takes 4 powers of this p to be a principal ideal, right? So the only way to disperse this out is this way. How about this one though? How many factorizations do we have here? So now instead of having a repeated ideal over and over again, you've got 2 different ones and you sprinkle them in forward. So if you make the following irreducible, Pi times P2, I'm sorry, P1, the I, P2, or minus I. Right, because these are all in the same class, so they turn into irreducibles in clumps too. Then basically, the factorizations you get right here are x2. I'm going to suppress the units here, up to units. This is alpha 0 times alpha 4, alpha 1 times alpha 3, and alpha 2 squared. So actually, I get 3 interesting factors here when I do it this way. How many here? I'm not going to list all of these. I'm assuming that the subscripted primes are all different, right? They're all distinct primes. There are actually 35 factorizations. Right? Because to make one, and they all factor into 2 irreducibles. Every factorization of this is into 2 irreducibles. And there's 35 of them because you're selecting your set of whatever it is, 8 choose 4, right? And notice, once you've selected your first set, it determines the second set, right? And so you probably get 70 divided by 2, because once you pick the first set, it determines the second. So there should be 35 factorizations, all of length 2. Notice so far, all the factorizations are length 2. What happens here? This one has 2 factorizations of length 2. And I think one of them 4. So here, let's just write down what these are. So you have, let alpha equal P1 to the 4, beta equals Q1 to the 4, and gamma is P1 and Q1. So, right, you get 1 of length 2 and 2 of length 4. This one. So you should check this, see if you can count this out. You get 24 factorizations of length 4 and 1 of length 2. And the length 2 is just putting these together like this. Notice the length 4 are extensive because like P1, Q2, P4, Q1, these are all irreducible. And finally, this one's irreducible, so there's only one. Okay, see if you can sort through that and make sense out of that. Check my combinatorics there and there. But this illustrates, I think, how the class group can really affect factorizations. There's all kinds of exotic things you can build out of this. Okay, any questions? Let me encourage you all to check out the math club today. It is, of course, the last math club until the last math club, which will be 2 weeks from now. But the last one before Thanksgiving, we have an undergraduate who's talking about an intern experience doing data analytics on baseball. So it should be a lot of fun. I hope to see you there. Otherwise, have a good weekend.